Wood. We see it pretty much everywhere, right? In our furniture, our homes, it's been with us forever. It feels so simple, so familiar. But behind that grain that we all know so well, there's this fascinating, really complex science that makes it one of the most advanced and, yeah, sustainable building materials we have for the future.
I mean, just look at this thing. It's so intricate, it's modern, and it's made almost entirely of wood. So how is that even possible? How can a material that literally grows on trees be engineered with this level of precision? What's the secret sauce that lets us build the future from the forest? Well, to find out, we got to go right back to the very beginning.
Everything, and I mean everything that makes wood a super material, starts right here, inside the tree. All of its amazing properties are a direct result of its biological blueprint, something that's been perfected over millions of years to grow tall and stay strong against everything nature throws at it. What you're looking at here, this cross-section of a tree trunk, it's basically its life story and its engineering manual, all rolled into one. Every single ring, every single layer, has a very specific job to do, and together they create this perfectly optimized structure from the inside out.
Okay, so let's break it down. Right at the very center, you've got the pith. That's the tiny little stem from when the tree was just a sapling. Around that is the heartwood. This is the tree's skeleton, its dense, strong structural core. Then comes the sapwood, which is like the living pipeline, moving water all the way up the trunk. And on the outside, of course, is the bark, the tree's armor. But the real magic isn't just in these parts. It's how they're all put together.
And this all leads us to one single, absolutely critical concept. It's a bit of a mouthful: anisotropy. Sounds complicated, I know, but the idea is actually super simple. It just means wood behaves differently depending on which way you push or pull on it. And believe me, understanding this one property is the key to unlocking its incredible potential. Here's the best way to think about it. Imagine a bundle of uncooked spaghetti. If you push on the ends of the bundle, it's surprisingly strong, right? That's what we call loading it parallel to the grain. But what happens if you try to bend that same bundle from the side? It snaps in a second. That's perpendicular to the grain. So wood is massively strong in one direction and way, way weaker in the other.
But of course, that amazing strength profile isn't the same for every tree. The forest is packed with this incredible variety of species, and for an engineer trying to build something, that variety matters a lot. So to make sense of it all, engineers use classification systems like this one. They basically group different species based on their natural strength. You've got your Group A woods like teak. These are the heavyweights, incredibly strong and durable. Group B is your reliable, middle-of-the-road category. And then Group C woods, like mango, are on the lower end of the strength scale. This whole system lets a designer pick the perfect wood for the job, making sure a structure is both safe and not over-engineered. Okay, now for all its incredible strengths, we can't forget wood is a natural product, and nature is not perfect. So if we want to use it reliably, we have to really understand its built-in vulnerabilities, the things that are trying to break it down. So, what can go wrong? Well, engineers are pretty much constantly battling two major culprits. One of them is invisible, and the other one, well, it's often hiding in plain sight. Enemy number one, the single biggest factor by far, is water. The amount of moisture inside a piece of wood can radically change not just its strength, but its size and its shape. It is, without a doubt, the most critical thing to account for in any wooden structure. The key idea here is something called the fiber saturation point. Now, think of a wood cell wall like a kitchen sponge. You can soak that sponge until it literally can't absorb one more drop of water. That's its fiber saturation point. Now, here's the cool part. As the wood dries below that point, the sponge fibers themselves actually shrink and get stiffer, and the wood gets dramatically stronger. In fact, just by drying a piece of lumber from, say, 30% moisture down to 12%, you can nearly double its strength. That's huge. Okay, so that's the invisible enemy. The second enemy is physical flaws. You see, unlike steel that comes out of a factory all nice and uniform, wood grows with a history, and that history can leave behind defects that really compromise its strength.
The most common defect you'll see is a knot. Really, a knot is just the ghost of an old branch that got swallowed up as the tree grew wider. The problem is, its grain runs in a totally different direction from the rest of the board. It completely disrupts that perfect bundle of spaghetti we talked about, creating a weak spot where stress can build up to dangerous levels. And then there's another serious defect called a shake. This is an internal split that runs right along the growth rings.
You might not even be able to see it from the outside, but it massively weakens the wood's ability to resist shear forces. That's the force of fibers trying to slide past each other. It's a hidden danger that can cause a sudden and total failure.
Okay, so let's recap. We have this incredible material, but it's kind of inconsistent. It's strong, but only in one direction. It gets weaker when it's wet, and it's full of natural flaws. So how on earth do we build safely with it? Well, the answer is pretty brilliant. You turn those flaws into a formula.
The solution is found right here, in these incredibly dense engineering tables that are just packed with data. I know, it looks super complex, but this is exactly how engineers transform an unpredictable product of nature into a predictable, reliable building material. They test, they measure, and they calculate everything.
And the main tool they use is a system of, well, you can think of them as reality checks or safety adjustments. The technical term is modification factors. So instead of just hoping every piece of wood is perfect, they start with a baseline strength value they get in a lab, and then they systematically reduce it to account for all the messy real-world conditions.
So, for example, they'll use a moisture factor. That makes sense, right? It accounts for whether the wood's going to be used in a damp basement or a dry attic. They also apply a load duration factor because it turns out wood can handle a quick, strong gust of wind way better than a heavy load that just sits on it for 50 years. And of course, they factor in the grade of the timber, which is a direct measure of those defects we talked about, like knots and shakes.
And this isn't just some abstract theory. I mean, applying these factors correctly is what makes a building stand for a century. It is the hidden science that makes sure the floor you're standing on is safe and the roof over your head is secure.
Which brings us right back to here. When you look at this stunning wooden structure now, you see so much more than just beauty, don't you? You see the science. You can see the careful thought that went into the grain direction, the specific choice of species, and all the math used to account for every single potential flaw and weakness. It's this incredible material that is somehow both a simple product of nature and a total marvel of engineering. So the next time you see a wooden beam, or even just a simple plank, maybe you'll see all that hidden complexity inside. Now that you know the science behind it all, will you ever look at a piece of wood the same way again?